Good evening, guys. I hope you guys are all good and that everything is okay. And I'm hopeful that you got the WhatsApp message that I've shared with you. Yes. Unfortunately, Mr. Makai is on leave this week, so we won't be having mathematics again this week. We're very sorry for that. So we shall proceed with physical sciences and continue with chemical equilibrium. Hopefully today we're going to manage to cover as much as we can in this topic so that we can move on to doing your acids and bases. And that will leave us with only Doppler's effect to complete the work for term 1 and term 2. I'm not sure if of the dates for your examinations. So I'm not sure if we're gonna be able to have time to do some revision before you guys go for your examinations, your half-yearly examinations. And yep, again, we encourage you guys to start applying to universities because, especially if you are interested in studying medicine, most of the universities that offer medicine, they normally, the closing date for registrations, rather for applications, is around June. So please make it a point that you do start as early as now to using your grade 11 results, apply for university so that you can secure the space well in time. And without wasting time, Rowena and Tulwana, once more, welcome you to our evening sessions brought to you by Sasol and Komatsu in collaboration with Osizweni Science Center. And of course, you already know my name is Sandile Vilane. And let's get started. So without wasting time, last week we introduced you to this concept of chemical equilibrium and we look at key things that are critical that you need to know. And we said reaction can only reach equilibrium provided this is taking place in a closed system. And then in a closed system, both the matter and mass are conserved. So we also said at equilibrium, the rate of the forward reaction equals to the rate of the reverse reaction, and the concentration of reactants and product remain constant. Then we looked at these two graphs, one which speaks about concentration versus time, and the other one which speaks about the reaction rate against time. So there were quite a number of things that we discussed, including the factors that affect the equilibrium position of a reaction, which includes temperature, concentration, pressure or volume, as well as a catalyst. So those are your 4 factors that affect. So remember what we said, catalyst has got the same effect, has the same effect on both forward and reverse reaction. So it will speed up both these reactions in an equal manner. And then we looked at quite a number of things such as, the effect of temperature on the Kc. We spoke about that. That's okay. If the increase in temperature results in the bigger Kc value, then we conclude that the concentration of the product was increased, which means forward reaction was favored, and therefore forward reaction is endothermic. That is basically what we discussed last week. And I want us to continue. Then we looked at this question, which was question 2, and then we did that, which ended here. And then there was a question from somebody who sent directly to my number, and then we also discussed this, the effect of decrease in concentration. So we shall proceed from here and then continue from what we have started. All right, I see no reason why we shouldn't continue. Those who are not here will join us later. So we just gonna shoot straight into doing. I want us to discuss this one question here. Yeah, look at this one. Question 10. We're going to come back to question 10. But I want us first to discuss, where is this question again? Starting with question 4. We'll see how many questions we're going to manage to finish. But let's start with this question 4. So in our question 4, okay, so this is a reaction, a hypothetical reaction, by the way. An unknown gas X2 is sealed in a container and allowed to form the extra gas at 300 degrees Celsius. The reaction reaches equilibrium according to the following balance equation. And then it is that 3 moles of X2 gas produces 2 moles of X3 gas. How will the rate of the formation of X3 compared to the rate of formation of X2 gas at equilibrium? We already know the answer here, isn't it? It will be equal. Rate of the forward reaction, formation of X2 gas, that's a reverse reaction. Rate of formation of X3 gas, that's a rate of the forward reaction. So at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And that is straightforward. And they say that the reaction mixture is analyzed at regular time intervals. The results obtained are shown in the table. So we are measuring the concentration of X2 gas against the concentration against time, as well as the concentration of X3 gas against time. But if we look from 8 to 10 seconds, look at these concentrations. These concentrations are now constant. And we said to you, once this happens, it means that at exactly 6 seconds, we have reached the equilibrium, because we say that at equilibrium, the rate of the forward reaction equals to the rate of the reverse reaction, and the concentrations of there is no net change in the concentrations of your reactants as well as your products. And 4,2, they want us to calculate the equilibrium constant for this reaction. So we can see that this is the equilibrium concentration of X2 gas, and this is the equilibrium concentration of the X3 gas. So since we already have that, it should be easy for us to say now, in question 4,2, we know the Kc value will be equal to the concentration of the products X3 gas to the power of 2, because the coefficient there is 2, over the concentration of X2, equilibrium concentration of X2 gas to the power of 3, because that is your stoichiometric coefficient. And this is your Kc expression for this reaction. The equilibrium concentration of X3 gas is 0,226. And I need you guys to help me with your calculators here. This is to the power of 3. And what answer do we get, guys?
So the answer is 236,46.
236,46 without the units. And that's it. That's a straightforward question I would like to believe. More X2 gas is now added. More extra gas. Hey, what is going on now? More extra gas is now added to the container. So we are increasing the concentration of this. And remember what we said. The reaction is in equilibrium. And then you've got your X2 gas and you've got your extra gas here. So if I increase this concentration by adding more of this, now this side will initially be disturbed, because now the weight has increased on this side. So what should happen now? Then to balance this, in order for this to balance, then the equilibrium position should shift to the right, or it should favor the reverse reaction. More of this is going to react to produce that in order to establish the new equilibrium. The new equilibrium. So more of the products will react to produce the reactants in order to relieve the stress and establish new equilibrium. So let us look at what is happening. How will this affect the amount of X2 gas? It will increase. How so? Because more of the reactants will now have to, the product will have to react. So they want us to explain this using the Le principle. So what happens? Okay, as the concentration of X3 gas increases, the system will respond by producing more X2 gas in order to oppose. Remember, the Leach's principle speaks about that. In order to oppose or to relieve the stress. I don't like the word stress here. In order to oppose the disturbance and establish new balance or equilibrium. So the reverse reaction will be favored. So remember that when you increase the concentration of your products, you are going to favor the reverse reaction. That is what I think we said last time when we were discussing these factors. We said when you increase, an increase in concentration of the product favors the reverse reaction. That is what we've said there. So an increase in concentration of reactants favors the forward reaction, but an increase in concentration of product favors the reverse reaction. And remember what we spoke about, and I try to find this. Okay, I want you to read this with me. Okay. Chemical equilibrium. Leach's principle states that when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. So what was the disturbance here? The concentration of the product was increased. What is the opposition of that? It is to increase the concentration of the reactants to counter oppose that disturbance. So please remember that we are opposing the disturbance that was initially created so that we can establish new equilibrium. And the next question, okay. The next question is as follows. I don't know if there are any questions, guys, before we proceed. Any questions, Rowena?
No, sir.
Tolwana, are you still good? All right, I suppose that's a yes, even though I didn't get any response. All right, let us now look at this question here, which is graphically question. Now they are, yes.
So when in a chemical equilibrium question, when they're giving you the temperature, do they just give it to you to like throw you off?
It will depend. You see, like when we started this reaction, we can always change because changing temperature is one of the factors that affect the equilibrium. And also it affects your Kc value. This one, the equilibrium is established at 300 degrees Celsius. So we are controlling the temperature. We are keeping it at 300 degrees Celsius. But later on, if you proceed with this question, at some point, they tell you that now the reaction is repeated, but the temperature is now increased. And how does that affect the reaction? There is your graph. So we'll get to that question. I think you will be fully answered when we get to question 4.5. But yes, the equilibrium must be established. The reaction temperature must be controlled so that it remains constant. Okay?
Okay, sir. Thank you.
Yeah, because otherwise, if the temperature changes, then that will affect the rate of the reaction. That will affect the equilibrium position of the reaction. Right, let's look at this one. The curves on the set of axes alongside not drawn to scale was obtained from the results in the table. Excuse me. Now the question is, how does the rate of the forward reaction compare to that of the reverse reaction at T1? This is not equilibrium, remember? So the rate of the forward reaction is not equals to the rate of the reverse reaction. Equilibrium is established somewhere where the concentrations are now constant. But at T1, the concentrations are equal, but the reaction is not at equilibrium yet. So how can we answer this question? How does the rate of the forward reaction compare to the rate of the reverse reaction? Look at the concentration of, remember, this is the concentration of your reactants. And this is the concentration of your product. And remember, Kc equals to the concentration of your, oh my, all over the concentration of your reactant. I don't know what is going on now. Sorry. And then you are looking at this. The concentration here, the concentrations appear to be equal. But anyway, before reaching this point, the concentration of your reactants is higher than the concentration of your products. So if this number here is bigger than this number, then your Kc will be smaller, which means the forward reaction is lower than the reverse reaction. Anyway, before these concentrations surpass each other. So if I'm looking at this, I'm seeing that the concentration of my reactants is higher than the concentration of my products. And what else do I notice? I am noticing that the concentration of the products is decreasing and the concentration of the reactants is increasing. So what does that tell you? If the concentration of your reactants is decreasing and the concentrations of your product is increasing, what does that tell you about these rates? Anywhere in between. Okay. All right. Let us explain it this way. Let's do it this way. These are your products. These are your reactants. This is the point T1. Now we want to compare the rates. We want to compare the reaction rate. Oh my, what's going on? We want to compare these reaction rates. So we already have that actually here. Let's look at this. I think we already have that. Aha, there we go. Look at this. Look at this graph. So this is somewhere where your T1 is going to be. So at T1, T1 is already equilibrium. So this anywhere before you reach equilibrium, look at what is happening. The rate of your forward reaction is higher than the rate of your reverse reaction before you establish equilibrium. Before reaching equilibrium, the rate of the forward reaction is higher than the rate of the reverse reaction. And that answers the thing. Let's call this one, this is somewhere the T1 according to the graph. Let me alter these numbers so that T1 is somewhere, and then this is X. So at T1, I haven't yet reached equilibrium. And what is happening? According to this graph, the rate of the forward reaction is above the rate of the reverse reaction. And that is what is happening. I think this one answers it much better. So before reaching equilibrium, the rate of the forward reaction will be higher than the rate of the reverse reaction. That answers your question. I don't know if you guys understood that. So before reaching equilibrium, rate of the forward reaction is higher than the rate of the reverse reaction. Now your question comes in, Gerowina, about the temperature. The reaction is now repeated at a temperature of 400 degrees Celsius. We have increased the temperature here. The curves indicated by the dotted lines were obtained at this temperature. So what has happened? Let's look at what has happened. We have increased the temperature. We've increased the temperature from 300 to 100 degrees Celsius. And how has that affected this? And then if we compare, look at this line, which represents concentration of your product. Compare it to this dotted line, which this is at 300 degrees Celsius. Compare this to this concentration of your product, now at 400 degrees Celsius. After increasing the temperature, the concentration of your product is now low, smaller. Look at your reactants. After this, now here is the concentration of your reactants at 300. Compare that to the concentration of your reactants at 400. So this is at 300 degrees Celsius and this is at 400 degrees Celsius. Compared to this, at 400 degrees Celsius, the concentration of my reactants has increased. So what does that tell me? It tells me that the formation of my reactants is the reverse reaction. This means that the reverse reaction was favored. The reverse reaction was favored. The increase in temperature will always favor the endothermic reaction. Therefore, the reverse reaction is endothermic, and that makes the forward reaction to be exothermic. Did you guys get that? Or should I repeat it?
Please repeat, sir.
Right. Look at your graph. Starting with your reactants. Let's clear this up. Oops. Let's clean this up. I'm gonna start with your reactants or your product first. This is the amount of your product at 300 degrees Celsius. But this is the amount of your product at 400 degrees Celsius. After increasing the temperature, the amount of product has decreased. So an increase in temperature did not favor the forward reaction because the concentration is now smaller. But if I'm looking at my reactants, concentrations of your reactants, look at that. This is the concentrations of your reactants at 300 degrees Celsius. But after increasing the temperature to 400 degrees Celsius, look at your equilibrium concentration of your reactants. So the increase in temperature has increased the amount of the reactants. An increase in temperature will always favor the endothermic reaction. So by increasing the temperature here, I have increased the amount of the reactants present at equilibrium, which means the formation of the reactants was favored. Remember, increase in temperature will always favor the endothermic reaction. Therefore, the formation of the rate of the formation of the reactants was favored, and that is the reverse reaction. Let us write that down. Tolwan. So to answer this question, 4,5, let us inform them that an increase in temperature, according to the graph, has resulted in the increase in concentration of reactants at equilibrium. So by increasing the temperature here, I have increased the equilibrium concentration of reactants. So what do we know? We know that an increase in temperature will always favor the endothermic reaction. And what does that tell me? It tells me that therefore I can conclude that the reverse reaction, which is a formation of your product, of your reactants, sorry, the reverse reaction is endothermic, because the formation of your product, the formation of your reactants is the reverse reaction. An increase in temperature will always favor the endothermic reaction. So if the reverse reaction is endothermic, we can easily conclude that hence the forward reaction is exothermic. So that's basically what we're gonna discuss here. Remember that your increase in temperature, the bottom line is an increase in temperature favors the endothermic reaction. That is a bottom line. An increase in temperature, sorry, I was supposed to write temperature here. An increase in temperature will always favor the endothermic reaction. So what do? We look at the graph and we compare the equilibrium concentration of your reactants at these two different temperatures. So when the temperature was 300 degrees Celsius, this was the amount of the equilibrium amount of your reactants. But after increasing the temperature to 400 degrees Celsius, now this is the amount. I have increased the equilibrium concentration of the reactants. Remember, formation of the reactants is the reverse reaction. Therefore, an increase, according to this graph, an increase in temperature has favored the formation of my reactants, which means the reverse reaction was favored. An increase in temperature always favors the endothermic reaction. Any questions so far? Any questions so far, guys? No question. All right, let's proceed then. Someone is requesting for a link. Then there is a last question here, which is quite simple and straightforward. The Maxwell-Boltzmann distribution curve represents the number of particles against kinetic energy at 300 degrees Celsius. Draw this curve in the answer book on the same set of axes sketch. Sketch the curve that will be obtained at 400 degrees, clearly labeled the curves. Obviously here what we expect is that by increasing the temperature, we somehow increase the reaction rate. That's a generic definition. So we expect this curve at 400 to have a lower peak, and it must have higher number of particles this side, and that would be the case at 400 degrees Celsius. Lower peak, and on the other, after the peak, it must be above the other one. Because somewhere here, this is where you've got your activation energy. So this is the number of particles that are colliding effectively to produce the product. And that is basically that. So that was a simple question 4. I don't know if there are any questions. I want us to look at another question before we proceed. I think there is a question 9, which I liked. Yes, question 9. There's this question 9 that I want us to look at before, but are there any questions so far? No questions. Then let's look at question 9. This question 9. Right. So this is our question. And hydrogen and iodine are sealed in a 2 cubic decimeter container. The reaction is allowed to reach equilibrium at 700 kelvins. According to the following balance equation, 1 mole of hydrogen gas reacts with 1 mole of iodine gas to produce 2 moles of hydrogen iodide gas. Give a reason why the changes in pressure will have no effect on the equilibrium. We discussed this last time when we're speaking about pressure. I think someone asked a question about that. The reason why is because in my reactants, I've got 1 mole of a gas, 1 mole of a gas. So it's 1 plus 1, which makes it 2 moles of a gas. And in your product, you also have got 2 moles of a gas. So it's because you've got equal number of gaseous moles in your reactants as well as in your products. That is the reason why. When you've got the same number of gaseous moles in your reactants and the products, then pressure will not have effect on the equilibrium position. So neither of the reaction, whether forward or reverse reaction, will be favored. They will both be equally affected by the pressure. So in this instance, we are saying that this is because we have the same number of gaseous moles in the reactants and the products. That is why. So when that happens, please know that pressure will have no effect. As we proceed to the next question, I hope that there is Unati. Unati, it's the first time I'm seeing you. Unati Mosibi. We welcome you, Unati. It's the first time I think I'm seeing your name.
Thank you, sir. Yes, I've just started joining the classes today.
Oh, we welcome you. We always engage in this. Where are you from, Unati?
You mean like where do I live?
Yes.
I live in Sebokeng.
Oh, Sebokeng. I've received a lot of responses from Sebokeng.
Yes, sir.
All right, let's proceed. This is the next question, which goes as follows. At equilibrium, 0,028 moles at equilibrium. Notice, at equilibrium, 0,028 moles of hydrogen gas, 0,017 moles of iodine gas are present in the container. And remember, this is the volume of your container right here. And they further go on to say, calculate the initial mass. They want you to calculate the initial mass of the iodine gas in grams that was sealed in the container. If the equilibrium constant for this reaction is 55,3 at 700 kelvins. So this is where now we do that table thing. Okay, let's delete it. This is where we look now at this table. And in this table, we look at the initial number of moles. We look at the change in moles. Change in moles is stoichiometric. And then we look at your equilibrium moles. And we then, remember your Kc requires the concentration. The equilibrium concentration of your reactants as well as your products. Okay, I've just remembered something. I've just remembered something. Somebody please remind me when we finish with this question. We have to talk about something very fascinating. Why do we not include pure solids and pure liquids in the equilibrium constant expression? Remind me to answer that question for you. Why do we not include pure solids and pure liquids in the equilibrium concentrations? Remind me. Rowena, I know when you do not forget. Okay?
Yes, sir.
Please remind me, why do we not include pure solids and pure liquids in the Kc expression? Please do. Right, let's look at that. Remember, we do not know what was the initial moles of this. So let me just use, I'm just gonna use A. I don't know how much of this, but I know for the fact, if you read the statement, they said you only seal the hydrogen and iodine gas in a container. Read this. You only seal the hydrogen and iodine gas when you started the reaction. So when we start the reaction, we have zero amount of the product because I'm just starting. I am just mixing these two gases in the reaction chamber. That is why initially for your products, there is zero amount of your products. And then change is about the stoichiometry. Stoichiometry has got to do with this coefficient. There's a coefficient 1. So 1x mole of hydrogen gas and 1x mole of iodine gas react. That is why you have a negative, because reactants are being used up. They decrease. The negative indicates the decrease in the amount of your reactants. And here you are producing 2x based on that 2. So that 2 is from the stoichiometric coefficient. This 2 is from the stoichiometric coefficient. That 1 is from that stoichiometric coefficient. That 1 is also from the negative because the reactants are being used up. Equilibrium moles. These will be my equilibrium moles. A minus X, B minus X, 0 plus 2X, which is just 2X. These are your equilibrium moles of each of these gases. But fortunately, somewhere, somehow, you were told that the equilibrium moles of hydrogen gas is 0,028. So you know that this is 0,028. And you were also told about the equilibrium moles of your iodine gas. They said 0,017. So this number, the exact value of this is 0,017 moles. So that means I can easily calculate this concentration. Remember, C is equals to N over V. So in your case, this is your equilibrium moles divided by the volume. They said 2 cubic decimeter, and that is 0,014 moles per cubic decimeter. And this here, what about this? This will be 0,017 N over V divided by 2. And what does it give us? 3,5, 1, 2, 3. No, it can't be 3,5. No ways. What is it equals to, Rowena? 8,5 times 10 to the power of negative 1, 2, 3. Ne? Am I correct? No, it can't be 8,5. Yes, it's 8,5. Am I correct, guys?
Yes, sir, you're correct.
Okay, thank you, Unati. And then here I've got 2x over 2 because I don't know what x is. So this remains as x over 2. There we go. We have our equilibrium concentrations now. Now let's go and formulate our Kc expression. We start with the concentration of your equilibrium concentration of the product. This is raised to the power of 2 divided by the equilibrium concentration of the hydrogen gas multiplied by the equilibrium concentration of the iodine gas. And what is this Kc value? You were given the Kc value as 55,3. Kc is 55,3. Let's do that. So I'm having 55,3. Equilibrium concentration of hydrogen iodide, we don't know, it's X. So it's X squared. Equilibrium concentration of this is 0,014. And the equilibrium concentration of the iodine gas, 8,5 times 10 to the power of negative 3. This will help us to calculate the value of X. So we're going to multiply both sides by this, so that at the end of the day, we end up with x squared equals to 55,3 multiplied by 0,014 multiplied by 8,5 times 10 to the power of negative 3. Can someone please assist us with the calculator? I don't have one next to me.
So it's 6,6 times 10 to the power negative 3.
6,6, exactly 6,6.
So do you want 2 decimals?
Yeah, give me as many as you possibly can. We're gonna round off. Remember last time we spoke about the effect of rounding off before reaching the final answer.
Yes, sir.
So what is it?
6,5807
5807 times 10 to the power of
10 to the power negative 3.
And what is the square root of that?
That would be 8, 8,11215,138
all right, 112, that's about fine.
times 10
Now
to the
that
power
can't be times 10 to the power of
negative 2.
negative 2. Aha. So what is this S actually? What is S? What is the exact value of X? X is actually this number here. We have calculated this number here. Okay, now that I know what X is, and remember what I want to calculate is the initial mass of iodine gas. Let me go to my iodine gas. B, the initial moles of iodine is this one. So I need to find this number of moles, which is B, so that I can use it to calculate the initial mass. And remember, how can we find that? We said that B minus X is the equilibrium number of moles of the iodine gas, which is actually 0,017. Now that we know what X is, let us substitute this value of X. And what do we get here? We're going to add from 0,017, we are now adding 8.112 times 10 to the power of -2. And what do we get there? What do we get,
10 to the
Rowena?
power -2.
Repeat that again.
9.812
812 times 10 to the power of
negative.
-2. Aha, these are the initial moles of the iodine gas. These are the initial moles of the iodine gas, but the question was calculate the initial mass in grams. So we can now easily do that because we have this. From the periodic table, can someone please confirm I2? What is the molar mass of the iodine gas from the periodic table?
Iodine is 127, sir.
127, thank you. All right. And when you multiply that by 2, it gives what? 254.
Yes, sir.
And then you multiply both sides by 254. What do we get?
24.92 grams.
24.92 grams. That's it. This is what was required. So this is the mass, the initial mass of the iodine gas that was sealed in the container, as you can see. So we have used everything that was given, that was at our disposal to get to this point. So we use Kc to calculate the value of X, and we use the value of X to find the initial moles of iodine gas. And then we use the initial moles of the iodine gas to find the initial mass of the iodine gas. Questions before we move on?
So was I supposed to ask you that question at the end of the lesson or now?
Yeah, we can answer it now.
Okay, so you said that we should ask you why we do not include pure solids and pure liquids in the Kc expression.
Ah, beautiful question. Let's answer that question. Let's answer that question. There is what we call ideal gas equation. So we'll start with that. From grade 11, PV is equals to nRT. But remember that N is equals to mass over molar mass. Let's do some maths. So this will mean PV will be mRT over capital M, which is a molar mass. And what if I divide both sides by the volume? What would happen? If I divide both sides by the volume, end up with P is equals to mRT over molar mass times the volume. But there is this guy here, which unfortunately Lucas don't talk about in physical sciences, but those who are doing technical sciences, we speak about this. This is a ratio called density. So this is a Greek symbol rho. Density is equals to mass over V. So we end up with pressure is equals to rho RT, which is a density, divided by the molar mass. Okay. No, I think I've pitched this a bit high for you guys. Let's lower it. Let's lower the standard. Let's put it at grade level. At grade level, we define this. Remember, your Kc depends on the concentration. C is equals to N over V, right? And then remember also that N is equals to mass over molar mass. This is your N divided by the volume. So you end up with that. And then again, you've got this, which is a density, rho over the molar mass. So you end up with this equation, very interesting. This rho is a density. Density of pure solids and liquids is constant. Density of pure solids and pure liquids is constant. But again, the molar mass of a substance is constant. Molar mass of a substance is also constant. So I end up with a constant divided by the constant, which means the concentration of pure solids and pure liquids is constant. And that is why. So the concentration of pure solids and liquids does not change. This is what this tells me. And if it does not change, what is the point of including it in the equilibrium concentration when this does not change? And that is the reason why we do not include your what we call pure solids and pure liquids in the Kc expression, because for pure solids and pure liquids, concentration remains constant. And that is the answer. It is for that reason that we exclude this. Okay? Did you guys get that?
Sir, can you please say it again?
Because concentrations of pure liquids and solids is constant. That is the answer. Okay? The reason why we exclude pure solids and liquids is because concentrations of pure solids and pure liquids is constant. It does not change. So as the reaction proceeds, the concentration of a pure solid and pure liquid does not change with time. Let's look at that. Listen, read that. The concentrations of pure solids, pure liquids, and solvents are omitted from the equilibrium constant because they do not change significantly during reactions when enough is present to reach equilibrium. That's it. That is what we're proving to you. So we are not just telling you this statement verbally, but we are also proving it without any reasonable doubt mathematically. So that is what I was doing here. I was proving it to you that the concentrations of pure solids and liquids, they remain constant. Why? Because they depend on the density and the molar mass. Density of pure solids is constant. Molar mass of any substance is also constant. Dividing two constants will also give you another constant. That is why, Rowena, we omit those from the Kc expression. So the answer lies there in that concentrations of pure solids and pure liquids remain constant. Something is disturbing my network. Okay, I hope you guys got that. Any questions before we proceed? No questions. Right. I'm working with our marketing team here at Osizweni Science Center. So we're gonna be sharing with you guys our YouTube channel. In future, we are going to upload the whole lessons. We are recording right now, I think you can see on the screen that it says recording and transcription. So we are recording this session. So in the next future, in the nearby future, I will be sharing with you guys our YouTube page, link to that. For every lesson that we have, we're going to upload it, the whole lesson on YouTube. So I will send you guys the YouTube link if you want to revisit the sessions. Or should you have any problem with your load shedding, you will be able to access the recording from the YouTube link that I will be sharing with you. Okay? So those are, I think that should you have happen to have missed something, then you will be able to replay it on YouTube, rewind it, forward it, and do whatever you want to do. So starting with this very same lesson, you will get it. I will communicate when it will be uploaded. Right, let's proceed to this question. The reaction rate versus time graph below represent different changes made to the equilibrium mixture. And then the reaction starting here, the reaction is already in equilibrium. Why? Because the rate of the forward and the reverse reactions are equal. What do the parallel lines mean? In the first 2 minutes, they simply indicate that the reaction is in equilibrium. Why? Because the rate of the forward reaction is the same as the rate of the reverse reaction. That can only happen at equilibrium. State two possible changes. I think we discussed this last time. One, if I'm looking at 2 minutes, 9,4, the obvious thing that I can say is that because I see that the reverse reaction was affected in the same way as the reverse reaction was, the forward reaction was affected. So because both reactions are equally being affected, I must have used a catalyst. One was used. And secondly, earlier on, we told you that pressure does not have effect on this equilibrium. Give a reason why changes in pressure will have no impact. Pressure will have no effect. And what do I see here? This very same pressure must have been increased because the graphs are going upwards. I must have increased, but they are rising up at the same rate. The two graphs are increasing at the same rate. It means that because they are going up, I have increased pressure. Was increased. Remember, how do we increase pressure? By increasing, by decreasing the volume. And those are the two possible changes that we might have been made. But let us look now at question 9,5. The temperature of the equilibrium mixture was changed at T equals to 4 minutes. I'm seeing my graphs going down. When the graphs are going down, they indicate that there is a decrease in temperature because the graphs are going down. But what has happened? This decrease in temperature has favored, because look at this, after decreasing the temperature, look at what is happening. Your forward reaction, your reverse reaction was favored because look at how far low, how far slowed down the reverse reaction was. So the reaction, the forward reaction, which is a solid line graph, was affected the most. So the reverse reaction was favored. We have decreased the temperature, and the decrease in temperature will always favor an exothermic reaction. Remember that. A decrease in temperature will always favor an exothermic reaction. So because this one was favored by a decrease in temperature, this decrease in temperature has favored the reverse reaction. A decrease in temperature has favored the reverse. Decrease in temperature will always favor what? The exothermic reaction. Therefore, the reverse reaction is exothermic. If the reverse reaction is exothermic, then the forward reaction must be endothermic. Fully explain this and fully explain the answer. So we must apply the Leschetizer's principle to fully explain this effect or this reasoning. The very same reasoning, 9,5, 1. Right, we tell them from the graph, what do we observe? A decrease in temperature. How do we know that it's a decrease? Because when we decrease the temperature, the reaction rate will generally slow down. Generally speaking, when we're discussing, remember we're doing the factors that affect the reaction rate. We said an increase in temperature will increase the reaction rate. Therefore, what I'm seeing here is a decrease in reaction rate. Both the forward and the reverse, they are slowed down. But the reverse, the forward, was affected the most. So that is what we see. The reaction rates are both slowed down. So we know that a temperature was decreased. Firstly, we know that temperature was decreased. Did they tell us that? Was changed. They didn't say how it was changed. So let us tell them now, how was the change? It was a decrease. Why? Because both the reactions are slowed down. So we know for the fact, we know that is point number 1. Temperature must have been decreased. Then, so what has happened? This decrease, we see that it has affected the reverse reaction the most, the forward reaction the most, which means it has favored the reverse reaction. So this change has favored, according to the graph, has favored the reverse reaction. And what do we say? Remember, a decrease in temperature favors the exothermic reaction. The exothermic reaction. So our conclusion will be that, therefore, the reverse reaction is exothermic. And if this is the exothermic, hence the forward reaction is end. Simple. Case closed. Any questions so far, ladies and gentlemen? No questions so far. Good, excellent. So that's basically how you look at this, guys. So you look at your graph. When this graph, reaction rate graphs are going down, whatever change was made, that is a decrease. Look at what is happening at 2 minutes. At 2 minutes, the graphs are going up. Whatever change that was made, it's an increase. At 4 minutes, the graphs are going down. Whatever change that was made, it's a decrease. That is why in question 9,3, 9,4, we have said at 2 minutes, there was an increase in pressure because the graphs are going up. So pressure must have been increased. But we have already said that pressure in 9,1, they're telling us that pressure will have no impact. Changes in pressure will have no impact on equilibrium position. Okay, 9.5.2. How will this change influence the Kc value? Choose from increase, decrease, or remain the same. Remember, temperature definitely has the effect on the equilibrium position. We said We said last week on Wednesday. Let me try to find that. I don't know what did I do now. Here it is. Effect of we said for the for the endothermic, the forward reaction is endothermic. The temperature was decreased here. Okay. If an increase in temperature results in bigger Kc value, then the forward reaction is endothermic. But what did we do, Tin? We didn't do that. So the increase in temperature will result in bigger Kc value if the forward reaction is endothermic. But now what did we do? Remember, your Kc depends on the concentrations of your products as well as the concentration of your reactants. So we have decreased the temperature. By decreasing the temperature, we have increased the amount of the reactant and decreased the amount of the product. We have favored the reverse reaction. Reverse reaction is the formation of your reactants. We have increased the concentration of your reactants and decreased. Let's make this practical. Let's say I have a fraction, maybe 3/5, and then I'm going to increase the denominator, make it 6, and decrease the numerator, make it 2. Okay, these are not equal, sorry. So I have decreased this and increased the other one. 3/5 is 0.6. 2/6 is 0.3. So this is exactly what has happened. The new Kc value has now been decreased. This was your initial Kc value. So what did you do? The decrease in temperature has increased the equilibrium concentrations of your reactants and decreased the equilibrium concentrations of your products. How do we know that? Because formation of the reactants is the reverse reaction and formation of your product is the forward reaction. So by increasing the amount of the reactants and decreasing the amount of the product, I have decreased the Kc value. For an endothermic reaction, a decrease in temperature will decrease the Kc value. Chemistry. For an endothermic reaction, a decrease in temperature will result. I can't find my page now. What has happened here? Okay. Hey, these pages are now mixed up. I don't know what happened. My goodness. Okay. Okay. I think it's fine now. Yeah. Hey guys, I don't know what I just did here. Hey, my page is lost. Hey guys, I've lost my page. What did just happen here? We done with this, haven't we? No. I think I found it. Hey, these pages are confusing. I think we were here. So yeah, guys, by decreasing the temperature, You are going to decrease, provided, first and foremost, provided the reaction, the forward reaction is endothermic. Forward reaction is endothermic. For an endothermic reaction, a decrease in temperature will result in a decrease in the Kc value. Okay? That is what is happening. What change was made to the equilibrium mixture at 8 minutes? Let's look at 8 minutes. Something was decreased. And whatever was decreased, the mixture, when they speak about the mixture, they speak about the content in the reaction chamber, which is your hydrogen, iodine, as well as hydrogen iodide gas. So what did we do? Something was definitely removed. What has been removed? This hydrogen iodide gas was removed. No, can you say that? If we remove hydrogen iodide gas, then we are going to produce more hydrogen iodide. No, we did not remove the hydrogen iodide. We have removed either the hydrogen or the iodine gas. Reactants, amount of reactants was decreased. How do we know that? How do we know that? Look at this. If you remove the reactants, if you remove your reactants, then you are going to produce more reactants. So the reverse reaction was favored the most. The reverse reaction is the formation of your reactants. Whatever change we did is a decrease because the graphs are going down. So we have removed the reactants. So what does the Lechetillas principle state? It says that by removing the reactants, you are going to produce more reactants. You must counter that which you have made. So by removing the reactants, you are going to produce even more reactants, thus favoring the reverse reaction. Questions? We're done with this question. Any questions from your side? No questions. Excellent. All right. I think we still have time for one last question. We are at 19. Look at this question number 12. I want us to look at this question 12. Very interesting, very fascinating. Question 12. I want us to look at this question 12. Very interesting and very fascinating, but all right. Biochemistry. Right, guys, let's look at this question number 12. And without wasting time, we're just going to deep dive into this. Right, look at this. The question is as follows. The equation below represents a hypothetical reaction that reaches equilibrium in a closed container after 2 minutes. At room temperature, the letters X, Y, and Z represent the number of moles in the balance equation. Remember, this X, Y, and Z in the balance equation, these are your reacted moles. These are your stoichiometric moles, reacted moles, or what we call stoichiometric moles. The ratio at which the reactants are reacting and at which they produce the products. For example, look at your Haber process. Haber process, or let us just look at the very same previous question. Look at this one. So here I've got, if this was the equation, then x will be 1 here because that is stoichiometric coefficient. That will be 1, that is 2. What does this say? Let us read this carefully, because the balanced chemical equation is a statement on its own. It says, this statement here, it says 1 mole of iodine gas must be mixed with 1 mole of hydrogen gas to produce 2 moles of hydrogen iodide. Okay, so I have to use this to find the letters X, Y, and Z somewhere, somehow. But let us proceed. We'll come back to that one. The graph shows the change in the number of moles of reactants and product versus time during the reaction. Define the dynamic equilibrium. Guys, definitions are on you. You know your definitions, so we're not gonna, it's not worth discussing. 12 core, use the information in the graph to write down the values of X, Y, and Z. Remember, we said these are the reacted moles, not the initial moles, not the equilibrium moles, but these are the reacted moles. So how do I find these reacted moles? I have to say initial moles. Okay, these are your reactants. Okay, did they give me any indication? But I know these are my reactants. This is the amount of A, initial amount of A minus equilibrium amount of A. That is the reacted thing. So this is 16 minus 8, which is actually 8. 8 moles of this. What about Y? Same thing. Y is of B. We look at the concentration, the initial amount of B in moles. Notice. So these are the moles indeed. So initial moles is 8, equilibrium moles is 4. So this will be 8 minus 4, which is equals to 4. And for your Z, in the same fashion, this is 12 minus 0, so it is exactly 12. 8, 4, and 12. That is how we found this. So according to this, the balance equation is 8, 4, and 12. But there is a catch. There is a catch there, ladies and gentlemen. There is a catch. So I'm looking at this ratio. A is to B is to C. I'm currently having the ratio 8 is to 4 is to 12. Remember, in grade 8 mathematics, we teach you about simplifying the ratio. Ah, there we go again. Sorry, guys, this thing is always doing crazy things. I don't know why. Now, I need to close this and start afresh. Right, start afresh, chemical equilibrium. Oh. Right, okay, let's proceed. I wonder why the screen always does this. Just goes out of orientation for no apparent reason. Right, let's look at that here. Now we know that, but this is not a simplified ratio because there is a highest common factor between 8, 4, and 12. So the highest common factor of 8, 4, and 12 is 4. So we have to simplify this ratio by dividing by the highest common factor here, which results in 2 is to 1 is to 3. Therefore, this will be your exact value of x. 2 is to 1 is to 3. 2 is to 1 is to 3. So don't just rush into writing this. So this is 2, this is 1, this is 3. I hope you got that. They are mixed at a ratio of 8:4:12, but that is not a simplified, that is not a simplest ratio. The simplest ratio is 2:1:3, which means 2 moles of this was mixed with 1 mole of that to produce 3 moles of this. This is what it means. And of course, notice that if you multiply this entire thing by the very same factor of 4, if you multiply this by 4, you end up with 8, you end up with 4, you end up with 12. You end up with that. But that is not how we balance equations. We need a simplified ratio. So this would be the correct thing. So 2:1:3. Right. I don't know if you guys are with me here. Not sure if you guys are with me here. Hey, this camera, why is it on now? Hey, excellent. Let's proceed here, guys. That was a very tricky question there. Definitely not difficult, but it was tricky. Calculate the equilibrium constant Kc for this hypothetical reaction at room temperature if the volume of the closed container is 3 cubic decimeters. We reach equilibrium after 2 minutes. So I have to calculate the equilibrium concentrations first in question 12,3. I need to calculate the equilibrium concentrations of your A, which is N over V. Number of moles at equilibrium. Now I have to look at the graph. At equilibrium, I've got 8 moles of gas A in a container that is 3 cubic decimeter. I don't think I want to simplify this ratio because it's going to want me to. I would rather leave this as it is. Equilibrium concentration of gas B, according to this, at 2 minutes, which is where I've reached equilibrium, I've got 4 moles of gas B. And at equilibrium for your gas C, the equilibrium concentration will be, the equilibrium amount of this is exactly 12. So I'm having 12 over 3, and that one fortunately is 4. So this is my equilibrium. Now I have my concentration, equilibrium concentration. My equilibrium expression will be the equilibrium concentration. Remember, we have said this will be 3 to the power of 3. And if you got your X, Y, and Z wrong, then that means your Kc will automatically be wrong. Gas A, equilibrium concentration of gas A is 8 out of 3, but this is raised to the power of 2. And this is 4 out of 3 raised to the power of 1. And, oh, sorry, what did I do? I want the expression first. And then we have said this is 4. We have said this is 8 over 3. And we have said this is 4 over 3. I don't know what answer you're going to get there. Let me check. 27 over 4. Am I right? I'm seeing a 27 over 4. Am I right, guys? No, it can't be 27. 9. 9.
27 over 16, sir.
Over?
16.
Over 16. Oh, 27 over 16. Excellent. 27 over 16. And what is that answer? The exact value of 27 over 16 is 1 comma?
1,6875.
6875. That is your equilibrium constant. And I believe that's a straightforward thing. This was the straightforward question. Right. There comes a question again. This question of constant of temperature always pops up. It's a third question, and we're still encountering the very same question of the change in temperature. At T equals to 4 minutes, the temperature was increased. Temperature was increased. Right, so what has happened after increasing the temperature? After increasing the temperature, we have favored the production of the reactants. So we have favored the reverse reaction. An increase in temperature will always favor the endothermic reaction. And the formation of the reactants, A and B are the reactants. The formation of the reactants is the reverse reaction. Therefore, the forward reaction, the reverse reaction is endothermic. The reverse reaction is endothermic. Again, the very same explanation that we have said, that we have mentioned earlier on, we have said that an increase in temperature will favor. Okay, sorry, before we read, that should be a conclusion. Firstly, this increase in temperature has resulted in the increased in the amount of the reactants. So by increasing the temperature, I have increased the amount. What does this mean? It means that the reverse reaction was favored. Because formation of the reactants is the reverse reaction. Rowena, are you sure about your 27/16?
So it's the second bracket on the denominator, 4/3.
Yeah, it's 4/3.
Yes, sir, then it's 27/16.
Are you sure?
Yes, sir.
But I say 27/4. How is that even possible? 4 cubed is 64. 8 squared is also 64. No ways.
No, sir,
Let me
it's right.
check. 9 times 3 is 27. I mean, I'm getting a 27 out of 4.
It's right, sir. I mistakenly squared the 4 instead of cubed it.
Aha, it's 27 out of 4. Okay, let's proceed now. Right, the reverse reaction was favored, and then we tell them that an increase in temperature will favor the endothermic reaction. And therefore, in this case, reverse reaction, which was favored by the increase in temperature, is endothermic. And that's it. And that's basically it. So which means the forward reaction is exothermic. And that's your question 12 right there. I hope you guys got that. Any questions so far? We have 30 minutes, we can still do more. But I think by now you guys are getting, already seeing the, we can close this with question 13. And then on Wednesday, like I said, I don't think you want to miss Wednesday's session. We're going to be doing acids and bases from a very different perspective. So please do not miss out on Wednesday. We're going to be doing acids and bases, guys. Believe you me, you don't want to miss even a single session of your acids and bases. We're going to lay a very solid foundation, big, but very solid. Right, question 13, which is our last question for the night. and for this chapter. Right, dinitrogen tetroxide decomposes to nitrogen dioxide in a sealed syringe of volume 2 cubic decimeter. The mixture reaches equilibrium at 325 degrees Celsius according to the balance equation. Dinitrogen tetroxide is a colorless gas, and nitrogen dioxide is brownish in color. When equilibrium is reached, it is observed that the color in the gas syringe is brown. When equilibrium is reached, it is observed that when equilibrium is reached, it is observed that the color is brown, which means there is more of nitrogen dioxide. State digital last principle in words. That one is on you, guys. Definitions are on you. 13.2, the syringe is now dipped into a beaker of ice water. We are decreasing the temperature. We are decreasing it. After a while, a brown color disappears, which means the decrease in temperature here. The brown color disappears, which means this favors the reverse reaction, because your reverse reaction is colorless. A decrease in temperature has favored the reverse reaction. Therefore, the reverse reaction is exothermic and the fourth reaction is endothermic. And you see, they always like asking you about temperature. They are still asking you about temperature. Again, the very same algorithm that you have followed, we're still gonna follow it to explain using the Leach-Tillers principle, 13.2. So what has happened there? Okay. Okay, dipping this, we tell them first, dipping a syringe in ice water is equivalent to decreasing the temperature. So this is what we highlight to them first. And then secondly, what has happened? So this decrease in temperature, has favored the reverse reaction, because the color of a gas, the brown color disappears, which means more of the colorless gas is produced, which is your reverse reaction, the reverse reaction. This decrease has favored the reverse reaction. So what does that tell me? We tell them that a decrease in temperature again favors an exothermic reaction. And then we can conclude. Therefore, the side which was favored, which is your reverse reaction, is exothermic. And that's it. So we've been discussing by now. I think you guys need to have seen how we go about doing this. 13.3, question 13.3. The volume of a gas is now decreased. Volume of a gas is now decreased, which means we've increased the pressure. While the temperature is kept constant, how will each of the following? So remember that when we increase, we've even shown, we played a very nice simulation of this using Java Lab. Okay. Let's do this first simulation for you one more time. One more time. Let's look at this simulated. No, not this one. Chemistry, chemical reactions. This one right. Okay, let's look at this. So we said to you in this simulation, what you see, this with the 2 yellow dots and 4 red dots is N2O4. So what did we do here? They said we've decreased. They're saying to us that the volume is now decreased. Look at what happens when you decrease the volume. In this first syringe, the volume is smaller. The space occupied by the gas is smaller. When the space occupied by the gas is smaller, I have more of N2O4 compared to when the space occupied by the gas is bigger. When the volume of the gas is bigger, you have more of NO2. So by decreasing this volume, look at what happens. When you decrease this volume, look at what happens. You are producing more of N2O4. Even here, when you produce this, when you reduce this, you end up with a lot of N2O4. And when you increase the volume, you end up with more of NO2. So a decrease in volume in this case is favoring the forward reaction. It is favoring the forward reaction. So let's come here. The number of moles of N2O4 is that, look at that. But we have said last time, before we get into that, when we were discussing the factors, we said that pressure, an increase in pressure will favor the site with fewer gas moles, the site with fewer gaseous moles. So an increase in pressure means decreasing the volume, will favor the site with fewer gaseous moles. So let me go to my balance equation and look at the site with fewer gaseous moles. An increase in pressure favors the site. There is one here. It favors this. So the amount of N2O4, as we have seen here also from the simulation, because that is exactly the same reaction. When we decrease the volume, look at what happens. You end up with more of this with 2 nitrogen and 4 oxygens. A decrease in volume produces a lot of N2O4. So this one here, it increases. The value of the equilibrium constant, no change. It will remain the same. Why? Only temperature can affect the Kc value. Only the temperature will affect the Kc value, not pressure and definitely not concentration. The rate of the reverse reaction, because I'm producing more of N2O4, the rate of the reverse reaction, it increases. That's it. That's it. So it favors the reverse reaction, the site with fewer gaseous moles. And then the last question, 13,4, which will be your, it will include OKC. Here, there is a lot of English that is very much unnecessary, if you ask me, because the trick is in understanding the English. Initially, X moles of N2O4 were placed in a syringe of volume 2 cubic decimeters. When equilibrium was, it was found that 20% has decomposed. It didn't decompose too, but it has decomposed by, this is the change. It has decomposed by 20%. Of the X moles of this thing, 20% has decomposed. Meaning at equilibrium, I'm gonna be left with 80%. of the initial moles. Number chemistry. So in your question 13,4, okay, this is where again we go back into doing that table. Our reaction is N2O4 gas. It composes to produce 2 moles of nitrogen dioxide gas. So we want to look at these initial moles, change in the number of moles, equilibrium moles, as well as the equilibrium concentrations. So I've got the initial moles there. I've got the reacted or the change in moles, and I've got the equilibrium moles, as well as the equilibrium concentration. Hey, what is that one? As well as the equilibrium concentration. Initially, X moles, when you are starting the reaction, you're not going to have any of the product. Why? Because, my goodness, because they said that you are sealing initially. This is sealed in a syringe. So initially, when you are starting this, you are just placing your reactants without having any of the product. So for your products initially, you'll always have a 0, because when you start the reaction, you are starting with just the reactants. They said that this has decomposed by 20%. So 20% of X has decomposed. So that at equilibrium, what do I have? I have 80% of X. And 80%, remember 80% is 0,8. So this has decomposed. Okay, before I do that, sorry, let us use your stoichiometry. 1 X mole of that will decompose to produce 2 X moles of that. The 1 comes from this stoichiometric coefficient. The 2 comes from this stoichiometric coefficient. So for every 1 mole of dinitrogen tetraoxide gas that decomposes, 2 moles of nitrogen dioxide gas will be produced according to the balanced equation. And that is stoichiometry of the reaction. At equilibrium, now I know that this is actually just 0,2 of that. And at equilibrium, what am I going to have? I'm going to have 0,8, which is 80% of X. Here, what do I have? I've got just 2X. Notice the difference between the capital X and that X that we use in mathematics. So at equilibrium, the equilibrium concentration C is equals to N over V. This is 0,8X divided by 2. And this is 2X divided by 2, which is just X. And this is what? 0,4 capital X. So what do I have now? I'm given the Kc value as 0,16. I'm given the Kc value as 0,16. Okay. Oh, notice, guys, notice that here we are saying to you that negative 1x is equals to 0,2 of capital X, which means X, the value of X is 0,2x. And notice again that you've got X there Therefore, this concentration here, which is equals to X, is also 0.2 capital X. Notice that. And then also remember, we can now write our Kc expression. NO2, which is my product with 2 moles, and N2O4 equilibrium concentration. You are given the Kc value as 0.16. So this is 0.16. We have calculated the concentration of nitrogen dioxide gas. We found X, but we just proved that X is actually equals to 0.2 capital X. So that is an equilibrium concentration of that. Divide by the equilibrium concentration of that, which is just 0.4 X. This is 0.04 X squared, because when you square 0.2, it gives you that. When you square X, it gives you X squared. Divide by 0.4 X. There you will divide 0.04 by 0.4 to get 0.1, X squared by X to get X. And you've got 0.16. And when you divide both sides by 0.1, you shall find that X is actually 1.6. And what was X exactly? X is the initial number of moles. That's it. That's it. That's it. I don't know if there are any questions. We have only 30 minutes before the end of our session. Are there any questions from your side? Oh, we are joined by Asanda tonight. I think the only Asanda I know is my Asanda. All right, so that's basically how we go about doing that, guys. So you're always gonna be keeping your eyes and always be on the lookout. Try to minimize the number of unknowns, and that's precisely what we've done. That's precisely what we have done. Beautiful, beautiful. Angazi, guys, are there any questions from your side? Because from my side, this is what I had in store for you. This is what I had in store. We only have got about 10 minutes before the end of our session. We only have 2 minutes before the end of 10, slightly over 10 minutes before the end of our session. So this will be saved, and then, okay, yes. This I'm going to save. So then we're gonna get this. Asanda, I will add you to our WhatsApp group. I'll send you the link to join the WhatsApp group where we share all the information that we've discussed. And then remember what I've said, guys, earlier on. We are now recording our sessions. This session is recorded, 1 hour 52 minutes long. This session is recorded, so it will be uploaded to the YouTube channel, to our YouTube page, a link of which will be shared. So if you want to revisit this session, for example, Asanda has joined us a bit later, you will be able to get the whole lesson on YouTube for you to.
So,
Yes, Onati.
can you also add me on the WhatsApp group?
Okay. I do not have your number. So what I'm going to do, I will try to, let me do this. Under the chats, okay, let me do this. Under the chats, you'll get a link shortly, which I'm copying now. The link to join the WhatsApp group. But you
Okay.
must do it before you leave before the end of this session. Because otherwise later, once you leave this meeting, you won't get the link. Okay?
Okay.
Make it a point that you do it now before we terminate the session.
All right, sir.
Okay. So where do I get this? It's coming just now, guys. Sorry. Okay, I've just sent the link. Please check your chat and tell me if you are able to access that link. Asanda and Unati, are you able to access the link? Can you guys confirm if you can access the link which I've just shared? Unati?
Yeah, yes, sir. I've just accessed the link.
Okay. Did you
Thank you.
manage to add yourself?
Yes, sir. I'm about to join now.
Okay, Asanda has added herself. I can see that.
Okay.
All right, and then I'm waiting for you, Unati. So as soon as we have uploaded this episode or this session, I'm going to alert you guys in the WhatsApp group, and then everything that we do is always shared. So this work here that we have done. Okay, I see you. You also have just joined. I'm going to be sending this to our WhatsApp group as well in PDF. I'm just converting it now to PDF. So you'll get these notes. Yeah, you will get this on the WhatsApp. And what else? That's about it for tonight, guys. Let's meet on Thursday. So on Thursday, we're gonna be introducing acids and bases. Like I said, you don't want to miss out. On Wednesday, not Thursday, sorry. On Wednesday, we're starting at 6 o'clock. Unati and Asanda. At exactly 6 o'clock, we started. So be there. You don't want to miss out. You don't want to miss out. We just want to show you how simple this topic of acids and bases is. We're going to be unlocking a lot of things, and then we're going to be doing a lot of beautiful things, talking about everything from titrations, neutralization, to everything in between, to hydrolysis of the salts. What is the meaning of hydrolysis of salts? Why do we need to hydrolyze the salts? Why do we do titration? What is an acid-base reaction? And all of those things. So guys, thank you for tuning in. If you have no questions, well, we're still at about 5 minutes, but I see that you guys are sorted. You have no questions. So we can call it a night. Thanks for joining in and enjoy the rest of your evening. Good night.
Good night, sir.
All right, enjoy. Bye.